Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, my students. So I decided to record this meeting today since that nobody come to visit my invitations in Zoom. So at this moment, I would like to continue my previous lecture regarding the second topic that I will talk about method and technique used in metabolomic analysis. So in the previous lectures, we have discussed about the basic principles and the concepts of metabolomic, including the difference between metabolite, metabolomes, and metabolomic itself, and the classifications of metabolites that could be endogenous and exogenous metabolites, and also the relationship between metabolomic and other omic levels, including like genomic and then transcriptomic and also proteomic. And eventually, we also, the last week, talk about the characteristic of or the dynamics of metabolomic. So today, the particular topic will cover several specific subtopics, including the workflow of metabolomic analysis. So it means that what you should do, the step you should go through when you want to analyze the metabolism. And also, there are two basic principles of methods in analyzing of metabolomes, including targeted and non-targeted method. So we will discuss about what the difference between targeted and untargeted metabolomic analysis. And for the third, we will focus on the techniques in analyzing metabolomic. So we will also discuss about chromatography and also combination between chromatography and mass spectroscopy, like it gas chromatography combined with mass spectroscopy or liquid chromatography. And also we will also discuss about what is the strengths and the limitations of such technique used in metabolic analysis. And at the last, we also will try to take discuss an overview in very general way about the data of metabolomic and how to understand about such a data and to interpret it, and how then we could combine it with the research, including in my case that I will discuss about the combination between analysis of metabolomic profiling in herbal medicines, and then we will confirm the effect of such a metabolites in curing the disease using animal models. So now let's start from this story that actually in previously have explained that actually in our bodily fluids, there are many kind of fluids, including like in our sweat, also cerebrospinal fluids, and saliva, urine, blood, and even feces, composed of various kind of metabolites that could be, dynamically changed over time. So, for example, in our blood, um, when we are fasting, it will be very different compositions of metabolites as compared with a feeding state, or during, for example, the morning when you are waking up, just wake up from your sleep, then when we try to collect for, your urine, and then we analyze it using metabolome, approach, then it will be different with the conditions about 2 or 3 hours later. So it means that the metabolites in our body, also in other species, of course, in the plants, will be very dynamically changed over times, and it's very sensitive to the many factors, including the feeding state, and also related with your activity, and also related with the situations of the environment surrounds you. And the why that we need to perform the analysis, like in this story, that in this red ginger, researchers from IPB University revealed that actually when you analyze, when you harvest these samples for metabolomic analysis between morning and afternoon, you will find exactly the difference in their profiles of metabolomes. So here we can see, for example, in this peak, there are certain substances that could be, different between the samples, the similar, similar samples that you collect at different times. This is during the afternoon, and this is you collect during the morning. Collect it during morning, and it will be, it exhibit the variations in the compositions of their metabolites. So it proves, it's a kind of scientifically proved that the metabolomes will, dynamically change from time to times and from one situations to another situations. And how we could quantify, how could we, you know determine such kind of the difference and also the dynamic change of the metabolomes in biological systems. So in this term I call biological system, it means that could be single cells, could be extracellular fluids, and could also single organs, or even organ systems, or even individuals. And so we only could reveal such a kind of difference, the dynamic change, by analyzing of the compositions, and also the identity and the compositions and the concentrations of any kinds of metabolomes detected in biological systems. So um, so this is the workflow that we should go through if we want to analyze metabolome, if we want to perform the metabolomic study. So it's quite simple step, actually, simple workflow. The first, but remember, the first thing when you want to do kind of the research or analysis in metabolomic, you need to decide the designs of your study. So that's a very kind of the preliminary step, that you decide what kind of experiment you want to do, what kind of study, whether you will explore um, the compositions without any kind of treatment or pre-treatment, or you will design certain kind of experiments. For example, in our case, we perform that experimental treatment to animal models, and afterwards, after several treatment, then you will analyze the metabolic profiles in the blood, plasms, and another kind, you may also just collect the sample from the fields, and afterwards you run the metabolomic analysis for such samples to reveal, like its secondary metabolic compositions and any kinds of metabolites. So after you decide what's kind of the type of your study, next, this is the major step is sample extractions, or I would like call it sample preparations. So in sample collections and preparations, you have to collect your samples, of course, in order to be able to analyze the metabolites in your samples. You have to collect it. So, for example, for animal models, you can collect the blood samples directly by sucking the blood from the heart, or sucking the body fluids, or you just collect the tissue samples, like from the liver or from the brains, or from any kind of a tissue. Or, for example, if you collect the samples from the plants, like you collect the leaves or the stems also. So the first step is sample collection. And after you collect the samples, then sometimes you have to deploy some method to uh, to prepare such samples. Like we can call it like extractions, or just separate your samples with any kind of other substances. For example, when you collect blood, then you will analyze, you will focus on the blood plasms, not the blood cells. So therefore, you have to collect the plasms. So in order to collect the plasms, you need to centrifuge that's a sample. So you run the centrifugations at certain speeds and times, and afterwards, your sample will be separated into two portions. The plasms, it will be, at the upper part, and the blood cells and any kind of, substance will be supernatant, native and supernatant, and then you will collect these plasms. So that's kind of also the step of sample preparations, including extractions. So when you want to analyze the samples that will, the solid sample, for example, like from tissue or from plants organs, like from the leaves or from the stems or even from rhizomes or from tubers, you need to run the the several steps in extractions, like when you want to extract the leaves from the herbal medicines plant, I mean medicinal plants. So you need to run extractions, and after you get your samples ready, you have this extract, you have this blood plasms right after what the preparations. Then the next step is how you will perform this processing by using the machine. So in this step, you need two different steps. The first, you need to separate the metabolite composed of that sample. So that's why the so-called separations. And immediately by separating it, you can also deploy the detections. So separations, you will separate it through like a different polarity, different blood. It's not blood, the different molecular mass and different volatility of such samples, and metabolite, and after what you need to detect it, what kind of this metabolite, and how to calculate the molecular mass, and eventually you will get information about the compositions and also the identity of metabolite in your samples. So separation and detections absolutely requires the processing device. Therefore, you need analytical machines. Like next, we will talk about like a chromatography combined with mass spectroscopy. And after you analyze your sample using these analytical machines by mean separation and detection protocols, then you will obtain your data by such machines. So what will you do? What should you do with this kind of data? You need to extract the data, and then you will process the data with certain kind of like any kind of software. So after you obtain the data, it's not ready yet to be used in your to interpret. So you need again to calculate a kind of the tendency and also the composition and any kind of the characteristic of such metabolites inside, I mean, contained in your samples. And that means the step is a part of the data extractions. So after you obtain the very clear data with any kind of the identity of the metabolite in your samples, then you also need again to deploy the the further step, including statistical analysis by comparing uh, the compositions, or probably the variations of structures as well, and also the concentrations between one sample to another sample, to um, to get a very clear overview, clear information regarding your samples. So this is the very general overflow. Here it is in this seems, as you can see that the first step that you need to collect your samples, like you collect sample from the tissue, for example, and also from the leaves or the stems of the plants, or also you can collect the samples from microbes. It depends on the kind of your study. So after you deploy the biological or tissue samples preparations, you need to do extractions, and then you will obtain the extracts that will be ready to be analyzed using this chemical analysis device. And after what you will produce the data, and this data are needed to be further analyzed. And eventually after you perform a proper analysis on your data, you will be able to interpret it for further applications. And this is also the very simple step that in sample collection, you need, for example, in study of disease and in like a whole study, you need to divide your samples between the disease group or control groups, or for example, treated or non-treated groups, and then you will collect a sample from your animal model or from your patients, including like urine, plasma, and tissue, etc. And after that you will prepare a sample for analysis for separations and detections, and then you will deploy the measurement of that samples, and the data obtained should be analyzed using any kind of analysis, including multivariate analysis. And uh, one kind of the information that you may obtain from as a result of data analysis is like you can define which kind of metabolite, particular metabolite, uh, will show the very high and very you know a particular characteristic of metabolite, showing the different identity or different tendency in their concentrations in your samples that could be distinguished particular situation between disease or health group, for example, or between A or B group. And you can then use such a kind of metabolite as a marker for identification. This is also similar for the sample preparations, and this is also for data processing. So remember here, I jumped to this next step that in data processing that you need several steps actually. So you need to deploy data pre-processing. So before you directly process the data obtained from your measurement using any kind of technology you use, you need also pre-process your data. So including the filtering, you need to filter, you need to separate these, uncommon or unusual data, and also you need to calculate the retention time correction, for example, and also you need to align the chromatograms or the graphs you obtain, and also detection on the peak of each chromatograms. And after you finish the data pre-processing, then here it is the preparation of data to normalize or scaling of the quantitative data, and then you will deploy statistical analysis, including multivariate or univariate analysis and clustering. And eventually you will obtain metabolite identifications and also the pattern of your samples as compared with other samples. And at the latter steps, it is like when you want to interpret your data and when to connect it, for example, in certain situations, like how this is progressed from one step to another step, you need to do the functional interpretations, including like quantitative enhancement analysis, or you analyze the pathway, the plausible pathway that may be involved in certain kind of the disease. And then you will conduct the metabolite profiling or mapping to eventually uh, uh, get the integrations of your data with other levels of omic, including with transcriptomic, proteomic, and genomic. So that's the workflow. So I'm previously talking about I talked about workflow, and later in metabolomic there are two basic approach or method in analysis of your samples. The first is untargeted method, and the second is targeted. So what is the difference between untargeted and targeted? So in untargeted method, you don't specifically aims your analysis to detect only single or a group of metabolite, but you perform analysis to screen and to to explore any kind of metabolite. For example, when I get a for example, I collect blood plasma from one patient, and when I do the untargeted analysis, a method for metabolomic analysis for these samples, I just run this sample analysis, and I just explore any kind of what kind of the metabolomes inside the samples, composed of the samples. So without any particular target. But if you, for example, using the similar samples, then you just, okay, I just need to quantify the level of creatinine, for example. So specific where a kind, where a group only focus on a group of metabolite. So in this kind, for example, when you collect some sample from the plants and then you just specify to quantify the level of flavonoid or the level of carotenoid in sample, and you will ignore any kind of metabolite that may contain inside your within your samples, and therefore you will then use only the particular technique to reveal the concentrations of flavonoid. Then you will never explore another kind of the other kind of metabolite. So it's kind of different. The difference between when you untarget it, you just explore it, whatever it is, and in for the target, you just target that specific metabolite. So um, when you perform untargeted, it will, it may bring you to the opportunity to see everything within your samples. What kind of metabolites that may contain in your blood plasma, for example. So sometimes you will get various kind of metabolite that probably unidentified yet. So the more unknowns when you deploy the untargeted, because you just explore any kind of metabolites that will be detected by the machines, then you will you will be presented by such data. But uh, but what's the method, what's the problem for this untargeted, that you will make confused because you will get a very high amount of the data. So for example, in my case, I sometimes running the metabolomic analysis. I mean, it's not metabolite analysis with for my sample using gas chromatography and mass spectroscopy. I obtain, you know, like 20 or 30 or even 50 kind of metabolites in single samples. So it's kind of confused to analyze it, and also to quantify, and also to identify various kind of metabolites. But when you deploy the targeted, you just then focus on certain kind. For example, you when you just measure carotenoid, then you will get a single graph showing the level of carotenoid in your samples, and then it can be easily interpreted later. Um, so this is uh, the illustration showing the difference between untargeted metabolic profiles and targeted metabolic profiles. So this is the similar samples that you will be analyzed using two different approach. So when you analyze your sample for untargeted metabolic profiles, you may deploy several lab kinds of approach, including gas chromatography, for example, or liquid chromatography or nuclear magnetic resonance. And here is the data. You may find this very crowded graphs with a crowded feeds, and each page represents a single kind of metabolite in your samples. And then you need to deploy a putative metabolite analysis, and also it could be used for pathway analysis, and also to interpret a biological process that may involve in your samples. But for targeted metabolic profiles, you just use limited tools, because you just need to focus. For example, you focus only on measuring the concentrations of alanine or tryptophan, certain kind of amino acid in your sample. So you just quantify the level of alanine or the level of tryptophan, and then you will get the quantifications of metabolite, and then you will validate it. So it will end up with a different kind of data obtained from your study between untargeted metabolic profiles and targeted metabolomic profiling. However, uh, there are very close relationship between the result of untargeted approach with a targeted approach, because by analyzing your data using untargeted approach, then you will obtain a global metabolic profiling, and this global metabolic profiling could be used to as a material for targeted or further targeted analysis of your samples. And it's mean that you can deploy both approaches, including untargeted, but it depends on what kind of the aims of your study. So it determines the method that it will be used. And here is, I think I want to say, show you this one. So later, um, in previous lectures, I also have explained it that metabolomic is really, really sensitive in term of time, or we call it time, more time sensitive than other army. Here are the illustrations. This women eating noodles. Then immediately after she swallowed the noodles, and the noodles enter the gastrointestinal tract, that then will be further digested by enzymes, and then will be absorbed by intestines walls, and then the nutritions composed of this noodle will then distribute in circular systems and reach plasms and also the tissue. So when we deploy the metabolomic analysis, we then will find the very particular noise of alterations of metabolism inside this woman's body. But when we deploy the proteomic analysis, you can probably find the very certain levels of, I mean, lower levels of alterations in proteomic, profiles, and probably there is no alteration in genomic level, because DNA will be stable and will be unaffected because of only consuming food. So in metabolomic technique, there are several approach, including chromatography and also spectroscopy or spectrometry, and also nuclear magnetic resonance. There's a kind of a different technique to separate and also to quantify the metabolite. Then the current technology try to combine it. For example, you combine between chromatography, gas chromatography, with spectroscopy, and therefore you make use the method of GCMS or gas chromatography combined with mass spectroscopy, or you combine like high performance liquid chromatography with mass spectroscopy, and then you will use machines in as a hybrid or combination between HPLC and MS. So there, this is, here it is the list of techniques used in metabolomic, the common techniques. Actually, there are many kind of techniques that could be used, but here I am showing the very popular. So in early like 1960s, Harding researchers performed the metabolite profiling. So he is the pioneer in metabolomic analysis. So he deployed gas chromatography in order to deploy the profile to review the profiling metabolic profilings of urine. So he collected the urine sample from the patients, and then he tried to run he runs the gas chromatography for the samples, and eventually he got the very quite sophisticated profiles of urines. So that's the very basic of metabolic analysis. And afterward, the technology evolved, and various kind of the technique then rise and develop it. So now we can use like nuclear magnetic resonance spectroscopy that we can quantify the samples as well as identify the characteristic of the samples, and also magnetic resonance imaging, and also infrared spectroscopy to quantify your samples, and also like I previously mentioned, that combination between gas chromatography and mass spectroscopy, or combination between capillary electrophoresis with mass spectroscopy, or combination between high performance liquid chromatography with mass spectroscopy, or LCMS, and also some researchers also like to use a FTIR or Fourier transform infrared spectroscopy, that you uh, when you focus on like alkyl or additional structures of your metabolites. So you may need this a kind of technique to quantify and also to identify your samples. And recently, nowadays, among all of this recent technique developed, um, researchers like to use the three common techniques, including liquid chromatography, gas chromatography combined with mass spectroscopy, or that's called GCMS and LCMS, and also proton nuclear magnetic resonance. So in our case, in our university, and also in my case, I deploy also gas chromatography combined with mass spectroscopy, or uh, hyperthermal chromatography combined with mass spectroscopy. This is the concept for chromatography. Here it is. I bet that you also did it in your laboratory activity. For example, you separate um, the photosynthetic pigments from the leaves, and you use paper chromatography. That's a very basic way, but it's similar, actually, similar concepts and uh, principles in analyzing your sample using chromatography. So you can eventually find the pattern. I mean, you can eventually separate your samples based on their polarity, based on their molecular mass, and also based on their uh, volatility. Which kind of the technique you will use to quantify your data, to analyze your data? It depends on the concentrations of probable concentrations of your samples. I mean, metabolite in your samples. So when you want to quantify the sample with high concentrations, you may use ELISA. So this is the enzyme linked immunosorbent assay. This is the common technique that you can use to quantify like hormones or peptide or even like cytokines in your samples, and also quantify, for example, free radicals, and also to quantify uh, any kind of small molecules in your sample with high concentrations. But when you want to analyze your samples with concentrations, lower concentrations like within micromoles, then you need to use, you cannot quantify it using ELISA because ELISA is very limited to high concentrations, like up to millimole. But when your samples is in micromole, it is better to use nuclear magnetic resonance or gas chromatography and mass spectroscopy. And for the very, very small amount of your samples, like in nanomole or picomole or even femtomole, you need liquid chromatography, mass spectroscopy. So um, the probable concentrations of your samples will determine what kind of the technique you will use. But please remember that when you use liquid chromatography, you will quantify from the very small amount, like in in picomole, up to millimole. It means you will obtain the very high amount of metabolite detected from your analysis if you use liquid chromatography instead of gas chromatography. So this is the illustration showing how the chromatography works, implying that this is your samples were composed of various kind of combinations of metabolite. For instance, you collect the blood plasms. Of course, in the blood plasm there are many kind of metabolites combined inside. Then you need to separate it, and at the same time, you also need to quantify it to identify what kind of this metabolites composed of your blood plasms. So you need to run your samples in this columns. This is alongside with the gas flow, like you use helium gas in your chromatography columns, and each metabolite will be separated based on their affinity to stationary phase. So this is mobile phase is gas that will flow through this column, and the stationary phase is mean that immobile phase that is uh, the matrix for examples that compose of these columns, and your sample will be separated based on their affinity to stationary phase, and when it has a high affinity to stationary phase, then the sample will be you know detected in very first, in a very early part of your analytical times. And when your sample is kind of a low affinity to stationary phase, then the metabolite will be detected later. So then in your results, like showing in chromatograms, you may find one kind of metabolite will be detected like in a very early, like a 1 minute running of this chromatography, you will find the samples, this metabolite detected. But another metabolite may occur later, like after 20 or even 30 minutes later. So here it is the diagram showing uh, how the gas chromatography works. That this is the gas, like high purity gas, and this gas will flow through the columns, and then after the columns should be heated using an oven, so to to alter the pace of your samples, like from the liquid to the gas, and then eventually you can detect the substance that contained in your samples, and the detector will work to quantify and also to detect the spectral and also to quantify and at the same time to um, define the characteristic of your samples. Then using a software, you will could obtain the characteristic and also the probable concentrations, relative concentrations of your metabolite. So previously, you know that there are three common technology that may use like gas chromatography combined with mass spectroscopy or liquid chromatography and also nuclear magnetic resonance. So here it is a summary comparing between GCMS, LCMS, and nuclear magnetic resonance. Uh, for GCMS and LCMS, you need to prepare your samples, like you need to deploy extractions and derivatizations. And also for the liquid chromatography, you need also desalting, you need to remove the salt, and also you need to filter your samples before, prior to measurement using this instrument or techniques. But for nuclear magnetic resonance, you don't have to prepare your samples. You then have to deploy the extraction protocol. So you just directly collect your samples and then you can run analysis using NMF, nuclear magnetic resonance. However, as you see here, the sensitivity for GCMS and LCMS, as I mentioned before, that it's higher sensitivity. You may detect your samples in very low concentration, like in from picomole to micromole. But when you deploy nuclear magnetic resonance technique, you just could identify, could analyze your samples in higher concentration from micromole to millimole. So when the concentrations of certain kind of metabolite in your samples is very low, like in picomole or nanomole, for example, you can't analyze it using this nuclear magnetic resonance. So you need to analyze it using the more sensitive technique, including LCMS and GCMS. And for the quantifications, for GCMS and LCMS, you need to standard. So you need to standard in order to compare it to the concentrations of your samples. But for nuclear magnetic resonance, you don't need standard. So you don't need a substance, for example, identify concentrations for standard samples because it will work with a linear response. And for specific advantages, that of course it high sensitive, and also we now the current technology provide us with standard library uh, in many kind of platform, and therefore we can identify directly of your metabolite based on your analysis result. And also for LCMS, it's also the advantage is high, also highly sensitive, and you will obtain very high amounts of metabolite based on this detection method. I mean, technique. So LCMS, when you analyze your sample using LCMS, you will obtain, you know, more various samples. I mean, various metabolite that could be detected as compared with GCMS. But for what is the specific advantage for NMR, nuclear magnetic resonance, that this is because you don't need to extract your sample. This means it is non-destructive. So you don't have to grain your sample. You don't have to make it a powder, or you don't need to combine it with salt. And so it is mean that your sample will never be destructed. So you just collect it and then you will analyze it directly with any kind of preparation. And and because your sample is non-destructed, so it will be very useful for replication later because your sample is still intact there. but in case of when you deploy LCMS or GCMS, your sample has been extracted. It is meant that it may degrade it or alters, and therefore it may then you know cause the different deductions results afterward because your samples change over times. And this is the specific disadvantage using GCMS, gas chromatography mass spectroscopy, that of course, in order to prepare your samples, you need to deploy extractions. And sometimes extraction is difficult thing because you need, say, for example, like grain it, macerate it, and then you filter, and then you, uh, deploy certain kind of fractionations, and eventually you find you obtain your samples, and it takes a time, and of course it's highly cost. So and also this GCMS is not suitable for heat labile and very high boiling point metabolite. Why? Because in this GCMS and LCMS, you need to heat up your samples. Like previously I showed you, here we need to increase the temperatures of instruments like up to 250 degrees Celsius. So under that treatment, certain kind of metabolite with sensitive with high level of temperature will you know will be destroyed, and therefore you cannot detect it by using this method. And also when your metabolite is has a very high boiling point, also quite difficult to detect it using GCMS because, for example, for like metabolite with up to 500 degrees Celsius boiling point, it is impossible to detect it using GCMS because it has a lower temperature than that's a boiling point. So you will never be able to detect such kind of you know your sample using this GCMS. So then for LCMS, the problem is there is ion depression effect. Why? Because you perform also heating up, and also there is also certain kind of um, alterations in your sample during this analysis using the machine, and therefore it may cause the depressions in the ion, and it could affect the identity of your samples. It's may sometimes end up with wrong identity of metabolites. And also LCM, based on LCMS, we couldn't obtain information about the structures. And similar with GCMS, LCMS also deploy the extractions or sample preparation with or invasive, I mean destructive approach, and therefore these detections could not replicate for the similar samples because this is kind of destructive detections. And what's the matter? What's the problem with nuclear magnetic resonance? Even it's employed that you don't need to extract your samples, you can directly deploy the analysis on your samples, but unfortunately, this is quite lower sensitivity, and your result may uh, show may depict the overlap peak, and therefore it will confuse you to determine the particular identity of metabolite. So later, I would like to explain about what we have done in our laboratory. So related to metabolomic analysis. So here it is, the white ginger, white turmeric. This is endemic for our islands. Call it curcuma sumatrana atau kunyit Sumatra. And recently we collect this from pesisir selatan, in West Sumatra. So about 2 years ago, my student Jihan studied this uh, metabolites of this from the regions of this curcuma sumatrana, and she extract it using ethanotic extracts, the sample preparation step, and then she run gas chromatography combined with mass spectroscopy for the extract for the ethanotic extract. So here it is, these results obtained from the analysis. As you show here, as you may uh, uh, take attention to this graph. This is a called chromatograms. Chromatograms. So GCMS chromatogram showing here the x-axis uh, define the retention times. So the time needed to analyze the sample. So in this GCMS, we deploy like 40 minutes analysis, and you see here that this first obvious fade, substantial fade occurs here, like at 16 minutes, and then later there are several metabolites also detected in other minute. Like here is at 22 minutes, there are a very proper peak here, and also this one, and later like in a 32 minute we also find this peak. So this is peak showing, so every single peak is uh, related to a single kind of metabolite. So when you count, for example, how many peak here, it could be uh, uh, you know define it reflects the number of substance detected, or the number of metabolite detected in your samples. So the higher the peak, the higher the concentration of this metabolite in your samples. And here's the result. This is the very common one. So we just going to list here and listed here nine metabolite detected by using this GCN aesthetic. And we find, for example, folyrenols and also glycerin and boldenone and also artemisinin. And based on GCMS, we also could define not only the name and also molecular mass and also spectral, molecular spectral, and also we can also define the group by combining, by using our obtained data with database like in PubChem. And also we can later define the probable bioactivity of uh, this metabolite. For example, folyrenols is belonging to the group of terpenoid or sesquiterpenoid, and this metabolite is important as antidepressants. And sometimes this is kind of untargeted because you just screen it and you try to explore what kind of metabolite that could be composed, that could be contained in these regions. And then after running this GCMS analysis, we can obtain the information regarding any kind of metabolite detected in here. And then this data could be used to uh, focus. For example, later I probably may only focus to deploy the targeted metabolomic analysis by quantifying the level of artemisinin with a different of locality or different sampling site or different treatment, then that's a called targeted analysis, because I just target artemisinin and I just compare it the concentration between one sample to other. But in this case, in our study case, here we deploy the targeted approach of metabolomics. And so I don't want to explain about this relationship between and later here it is in another study recently. I have a joint research with a researcher from North Sumatra University and also from Indonesian University. So we focus on revealing the metabolite profiling of Ficus gracilis. So this is a kind of white grade, uh, uh, locally named Gagatan Harima from North Sumatra. So Ficus gracilis, I tried to collect the leaves and then I dried it up and I prepare like when you prepare the tea, and then we call it decoctions. And we when we deploy liquid chromatography mass spectroscopy, we obtain this data showing various kind of metabolite detected in this, decoctions of these leaves. And here it is, this y-axis showing the concentrations, so it's related to the concentrations, and here x-axis showing retention times. So we find some substantial peak showing the higher peak like this at minute 4. We also find this metabolite with high concentrations, and also running time, a retention time of 5.45 minutes. We find this substance, and lately up to 20 minutes we detected like this, in 17 minutes later another metabolite occurs here. And after analyzing this data, this chromatograph, we then reveal that actually there are 26 of metabolites could be detected using LCMS in this leaves of Fitis gracilis. And this is the identity like retention times and present area showing the relative concentrations of the same metabolites. And also this is the mass, molecular mass, and also molecular formula, and also the compound names. And based on this data, then we can use it as supporting data to another experiments, and also probably combined with another method of metabolic analysis. So I just want to show you that based on method and technique. So we have deployed to analyze the metabolite profile of this herbal medicines, like this medicinal plants commonly used by Karo tribes in North Sumatra for as a supporting stamina. And then here's like a highlight for our results. So I then investigate this protective effect of this leaves against the diabetes. So here it is, the diabetes of mice models, so animal models. We inject the alloxan in order to make it suffer of diabetes. And as you show here that histological alterations is, profoundly cures in diabetic mice in testicles tissue, showing that destructions, this is a very severe destructions in tubulus seminiferus in this testicle tissue. But when we at the same time treat our animals, the diabetic animals, with lower concentrations of Fides gracilis lip decoctions by daily basis, and we can see here that actually the Spitz gracilis with many kind of metabolites, showing the protective effect against the diabetes into the destructions of the testicle tissue. And you see here that there's a span here showing like close to the characteristic of tissue, testicle tissue in healthy mice. And but unfortunately with higher concentrations of this decoctions like 100 gram per liter, it's very high concentrations of Fetus gracilis samples we use. It also unfortunately cause the very severe destructions in testicles. So here it is that lower concentration is better to protect your testicle against diabetes. But high concentrations of this Vitis gracilis decoction can cause a very toxic effect on your testicles. So it could be related with some metabolite. For example, here's phosphoric acid detected in this Vitis gracilis leaves. So phosphoric acid actually is a toxic for testicle. It could destroy the testicle. But why in lower concentrations that it uh, its negative effect is we couldn't observe it because probably phosphoric acid at lower concentration couldn't affect it, and many kind of other substance function to protect your testes like some antioxidants and like here for example fatty acid that may um, also function as a protector for our tissue against diabetes. So I think that's all the latest up to date. And uh, at the last, I would like to explain about your individual talks. So please remember that next week you have to submit individually to answer these five questions. The first, please explain the workflow of metabolomic analysis. So based on my lectures, please clearly explain and draw the outline, the workflow of metabolic analysis. And later, the second question is, what is the difference, the particular differences between targeted and untargeted method of analysis in metabolomy. So, as I have explained before, if you just listen and understand well, then you can answer these questions. And the third, also please explain the basic principles and the procedures of analysis of chromatography and spectroscopies, mass spectroscopies, and metabolomic analysis. So, including how the procedures and basic principles of gas chromatography combined with mass spectroscopy, and also the liquid chromatography combined with mass spectroscopy, and also how the procedures for nuclear magnetic resonance. And later, the question number four, uh, what is the advantages and disadvantages of using liquid chromatography, mass spectroscopy, gas chromatography, and mass spectroscopy, and other technique, including nuclear magnetic resonance? And the last question is, uh, what is the data that could be revealed by metabolomic analysis, and what is the meaning of retention time, peak, and relative area? uh, Focus on chromatogram, of course. So please answer these five different questions individually, and write down using your pen, not by typing, because I need you to write it down by yourself. And then please submit your paper uh, on in likely at December 7th next week. Just collectively submit it through your you know friends or coordinators in your class and submit it to me, and I will evaluate it based on your answers on this individual talks. So I hope you remember this individual talks. And later, at that next meeting, this is the last meeting, please divide your class to five different groups. So please divide it by yourself to be five different groups. And then what is your talks is you need to prepare the poster. So you need to prepare your poster with a certain topics, including so our next topic is about the applications of metabolomic in many fields. So including how metabolomic could be used in conserving biodiversity, and also in agricultures, in fisheries, and also in husbandries, and also in health science, including like disease diagnosis, prognosis, and also drug developments and drug resistance, and also in forensic and as well as bioenergy processing. So please prepare your poster. Each group will talk about a different form of application. So there are five different topics here, different form of applications of metabolomic. So please, each group prepare the poster. For example, you may focus on forensic applications, or application in biodiversity conservation. So just prepare your poster nicely and clearly based on your explorations on reference in website, or also through library. You can obtain such kind of material for your poster, and prepare your poster in white paper, white and white color paper. Then later I will also send the files dividing the uh, uh, instructions for preparing your poster for the next week. I think that's all from me. Thank you very much for your attention for my lecture, and I hope that you can understand any kind of topic that we have talked today, and hopefully we can continue for the poster presentations next week. Assalamualaikum warahmatullahi wabarakatuh.